Log on, tune in, find out. Another good idea from Cambridge.
Great pleasure to welcome John Thompson to give his talk. He's going to talk about an action of SL2Z on the space of Dirichlet series and some associated computations.
Thanks a lot. Now, as I understand it, I mean, various ones of us are sorry that Jeff Robinson is not here. He would have definitely given a lecture if he'd been able to come, and I'm sure he was very appreciative of what the things Sarah had to say yesterday about Jeff's thinking about the amalgams that he's been playing with, really. And if he had been here, I don't think I would have lectured really. I mean, I have a sort of a full schedule. But anyway, I'm happy to talk, and I would like to say and make a general remark, which many of you will appreciate. So it's sort of my idea about mathematics and life in general, really. And it's very, very simple, really. You either use it or lose it. And I'm trying to use it. But the reasoning is, you think of the incredible structures that have been built in the mathematical world. It's asking an awful lot of young people to try to master all this material. And one way to suck them in is to have such nice results that they want to find out how the thing works themselves. So I think that motivates several of us. And so the things I'm going to talk about today, at least in my way of thinking, it may not be worth too much, but it's very natural. The things that I'm going to talk about they just unfold in a very natural way, and that I think is in itself is a it's not an argument that it's really worth anything, but it does put a certain context on things. So I want to mention, since I'll be talking about not talking about, but mentioning really, I'll leave it to Peter Sin to justify the references I will make to some computer calculations. Those of you who know about computers may want to query him and see how we came upon these striking things, really. But I will start in a fairly general setup with a partially ordered set. This game I'm playing can be played in many ways. I happen to push it in the direction of the zeta function, but there's certainly other ways you could play the game. So we have a partially ordered set, and from that one gets a map from S cross S into a two-element set. Now the two-element set that is usually used in talking about partially ordered sets is the set consisting of 0 and 1. But I don't like that. I don't like to put that restraint on it initially because there are cases when it's better to use a different set. So I'll just start off with a two-element set consisting of yes and no, really. And this is the measuring function that says that S T goes into yes, no, else. Okay, so this is the bare bones of any partially ordered set, and even in the case when one is interested in more or less standard incidence matrices, 0 and 1 may not be the only pairs of integers you want to consider. And I mention that not to be facetious. I'm not going to really make much use of it here, but I have seen examples of where it's worthwhile to take different pairs of integers. Now, so the special case that I'll be talking about could include a number of things. I guess the thing that leads most directly to the zeta function is the partially ordered set on the integers with divisibility. Meaning the partial ordering. With the same degree of generality, instead of taking the integers, one could take the set of non-zero ideals in the ring of integers of any number field. And again, you use set theoretic containment of one ideal being contained in another. And pretty much the same sort of game gets played, really. Right, now, so then when we do this, I'll introduce the standard incidence matrix, Dij, where Dij equals 1. So this thing's been around quite a while, this divisor matrix, and there's a certain amount of literature on it. My interest in it was aroused by the following consideration. Of course, this is you can think of this as an infinite matrix indexed by n cross n. And it has the property, the property I will focus on right away is that each column has only finitely many non-zero entries. That's because a given integer has only finitely many positive divisors. So these are sort of infinite matrices that are sort of what we call column finite. And one can then introduce the massive group, which I will just call GL infinity, of all the column finite matrices indexed by n cross n, which are invertible. So that I mean. That's well, it is a group, and the element D is in that group. And here's a general procedure which I see functioning in almost every lecture that I go to, really. That is, if you have a group and a subgroup, then it is very natural and often very productive to imagine, well, we can imagine two things. If you have, well, you can imagine many things. Well, let me just say what I'm going to head toward now. You have a group and a subgroup. Then the very natural thing to consider is the set of intermediate subgroups. If you think there may be a very small subgroup contained in a very big group, but then there's possibly a wealth of subgroups. Now, in this setup, we have this matrix, which is some sort of generalized unipotent matrix, upper triangular matrix with ones down the diagonal. And so it generates in this GL infinity an infinite cyclic group. And so the thing I started playing with several years ago now was what are the subgroups? Are there good subgroups that contain this thing? There are plenty of free groups. You can embed in a free subgroup of rank 2 if you want, or any other rank. And you can even do this in a way that it's a kind of group that was studied by Magnus, sort of a free, we call it a free nilpotent group. There could be quite some non-trivial invariance in that procedure. Well, but the thing which got my attention was my feeling about group theory of the absolutely central role, unavoidable central role that SL2 plays. I mean, you certainly can't wiggle in a finite group theory without coming across SL2. And so I asked, I started with an even easier question. You have an infinite cyclic group. Can you embed this infinite cyclic group in an infinite dihedral group? So you need to hunt for an involution in this column finite group that inverts the divisor matrix. And so I fooled around with that a bit and found such an involution. And Peter's also found such things. I haven't played too much of this involution, but I did play with it a bit. And I thought that should be recorded. But then the next step was try to embed so I'll call SL2Z gamma, and I'll try to embed the divisor group there, and it's such that D goes to the standard unipotent matrix, so the standard translation in SL2Z. And this is a completely natural thing to do, really. I mean, especially since this gadget here is, if you look at it, you see that it's doing the best it can in an infinite dimensional space to be unipotent. Well, anyway, this led to some fooling around, and eventually, yes, you can do this. It works. So we get map rho from gamma into this is a rho of D equals T. So this is the matrix representation, which I constructed some time ago now, several years ago. And I did it by trial and error, of course. And the first things I tried didn't work really, and I thought maybe I wasn't going to make it until I realized that the gamma has a very nice presentation. sorry, see if I can get this right. So this is a standard thing. It's a free product of a group of order 2 and a group of order 3 with a subgroup of order 2 amalgamated at the bottom. So, and this, I don't know how far back this goes really. I saw this many years ago, of course, as a graduate student. And so when you think of the group by generators relations, in a way it makes it easier to do certain things. So the construction of rho, in fact, produces rho of R and rho of S such that rho of S to the fourth equals 1 rho of R cubed equals rho of S squared equals minus the infinite identity matrix. So this particular representation is keeping track of the abstract presentation, which is good in some ways, maybe not so good in others. But the reason I did it wasn't because of any grand thing. It seemed natural, and furthermore, if you try to find these relations in an infinite group, it's easier than finding a random element of order 4 and a random element of order 6. So I mean, these aren't random. I mean, and rho of gamma is contained in GL infinity of the integers. So the matrices that occur here are integer matrices, and that has to be good, really, although it's very scary, really, because you have to start thinking about congruence things and stuff like that. Right. Now, so I had it in that stage for a while, and GL infinity acts on the space of sequences of complex numbers on the acts on the right, and it acts on the left of a vector space of countable dimension. It's the space of all column vectors with only finitely many non-zero entries. Here, when we act on the row vectors, we must take arbitrary sequences. So this is an example, a meaningful example, of where the relationship between a space and its dual space, they're quite different creatures. So anyway, we have this action, and I was wondering how this row of gamma acts on the space of sequences here. And well, I was unable to show that the rate of growth of the coefficients in rho, the matrices in this group rho of gamma, how fast do these coefficients, the matrix entries grow really? And Peter found a really lovely argument that shows that, so sin, so before I put that in, so we consider Dirichlet series. I'll call them Dirichlet sequences because there's really no Dirichlet series till you introduce them. These are sequences C1, Cn, such that Cn is less than, say, A, times n to the A, or positive, some positive A and A. So this is a growth condition. Sorry. That would be a Dirichlet sequence, and if you have a Dirichlet sequence, then the associated ordinary Dirichlet series does in fact have a half plane of convergence. So that's the role of this inequality, really. So Peter sin rho of S, rho of gamma. I put an S there, but sort of by mistake, really. But it wouldn't be really a mistake if I had left that with S, really, because the deciding factor of whether or not this group stabilizes Dirichlet series is given by the matrix S, rho of S, Peter sin. So this stabilizes okay, so I have that really, but, and there's a nice combinatorial argument. It depends on some numbers which Sayre has told us we were pretty naive, but we still are very naive. It was the Catalan numbers. We came across the Catalan numbers in constructing this thing, and the one knows about growth rate of them. And anyway, it's not a completely straightforward argument. It's a lovely combinatorial argument that Peter cooked up. And so we have these matrices now that stable the Dirichlet sequences, and hence then by a slight abuse, it's not really even abuse, just a convention, we have an action of the modular group on the vector space, the complex vector space of ordinary Dirichlet series. And so let me just mention a lemma here. Ordinary Dirichlet series. Then I mean, well, I just meant that we have these are series. If we have our, see, we had the Dirichlet sequences. So these are just the sequences with a growth condition. And the ordinary Dirichlet series associated with that is series Cn n to the minus s. I might say that that Peter and I have looked at a couple of papers of Bohr, Harold Bohr, who studied more general sequences and wrote a couple of beautiful papers on the behavior of the zeta function in the domain of convergence. But I mean, and he wrote a whole book on more generalized Dirichlet series. But these are the ones that we're playing with. So suppose we have an ordinary Dirichlet series, then the module f rho of gamma. So we're just taking a single series now and look at the module generated by such as, so we take our f and we hit it with the elements of this rho representation. And the module as module over the time being, we just work over the complex number. So we take the f of rho of G for G ranging over the modular group, take the linear combinations of that with the complex coefficients, and is contained in the ring C bracket F zeta F rho of S. So zeta is the Riemann zeta function, which the whole game has been cooked up to bring the zeta function in this way. And so another remark about ordinary Dirichlet series, they form an integral domain. And even though the reciprocal of a Dirichlet series, not necessarily a Dirichlet series, but the Dirichlet series themselves form an integral domain, and so one could talk about the field of fractions, even though when you go to the field of fractions, you lose the condition of having Dirichlet series. And no, I can't. No, I can't. I mean, it's pretty. I would. I mean, you yourself yesterday said, well, you do certain things, you're bound to make a mistake. And I would almost certainly, unless I just slavishly copied it out. I mean, I could have done a transparency and say this is it, really. But no, don't bug me about that. I can't. No, we have. I mean, it's not hand waving. It exists. It exists, and I like it a lot, really. But I don't want to dwell on it here. I wanted to get to this little lemma, really, and now what does that mean? What's the implication of this lemma? Well, we have our module sitting inside this ring, which is an integral domain, and it's generated by 3 elements. It has a field of fractions, that integral domain, and hence has a transcendence degree. Now, the transcendence degree of this field obviously is at most 3, because and it's at least 1 because the zeta function is a transcendental function. So here's a question that I have been thinking about quite a bit, really. What is the transcendence degree of this thing? Is it 1, 2, or 3? Now we found an example by taking f to be the constant function 1. The Dirichlet series takes the value 1 every place. Look at that module. So it's generated by 1, zeta, and the constant function acted on by rho of s. And that turned out to give us an elliptic curve. So it's a field of transcendence degree 1, whereas it could well have been transcendence degree 2. I mean, as far as we could see, really. And so we've been thinking about this elliptic curve, I don't think it's in such a very profound way, but still thinking about it. And I asked myself the question, do there exist ordinary Dirichlet series F such that this ring has a field of fractions which is not only of transcendence degree 1, but is actually of genus 0. From a certain point of view, you could say elliptic curves are the first incredibly important step up from fields of rational functions. And so here, I would really be happy to be able to prove that this ring is never a rational function field. And I don't know whether this is hard or not. So test cases. There are two basic test cases, I think. Possible genus 0 fields. That is to say, transcendence degree equal 1, genus equal 0. Now the two cases which I think in a completely natural way are, one of them is to some extent considered in the literature. So case 1 is f equal the square root of the zeta function. So the field generated by the square root of the zeta function, and zeta obviously is the genus 0 field. And the coefficients of this square root of the zeta function no longer integers. You get powers of 2 in the denominators. So that's already some danger signal. But anyway, that's case 1. Then case 2, which is a more generic case, f is an eigenfunction for rho of s. Rho of s is this matrix of order 4. Its square is minus the identity. So its eigenvalue is either I or minus I. And you can write down, of course, trivially, you can write down the Dirichlet series, which are eigenfunctions for this rho of s. And if you took such a thing, then this and this would be linearly dependent because this one is just plus or minus I times that one. And so you certainly know that the corresponding field has transcendence degree at most 2 because you just tack on the zeta function. So if there are I mean, I'd be quite happy to know this cannot happen. And I leave it there, really. Whether it's a manageable question or not, I can't answer that. I just don't have enough knowledge of the situation. Have I thrown away the black? Here it is. So anyway, so that's the transcendence degree question. And now I'll spend the rest of the time, I guess, probably, talking about this elliptic curve, which is a massive world in its own. It's a massive, big world in its own, but it's still only a small piece of what this game is about. So now take f equal to constant function 1 and set phi equal 1 rho of s. Then we get the defining equation. We get our elliptic curve, and the equation that comes out is zeta minus 1 phi squared plus zeta phi minus zeta minus 1 equals 0. So this is an equation which holds for all s in some suitably far to the right half plane, really. And Peter and I have not succeeded, even with that lovely work of Harold Bohr, in determining what the abscissa of convergence of this gadget here is. It may not be too tough, but we couldn't see how to do it. Right, now, so I fooled around with this thing for a while and didn't really do much of anything with it. Studied some coefficients, stuff like that. And then inevitably, really, when you have something like this, you are led to the Taniyama-Vey theorem, this fabulous theorem which links up elliptic curves defined over the rationals in a way with modular functions, algebraic extension, certain algebraic extension fields of the field generated by the J function. And so obviously you can't turn down something like that. It's just too fundamental. And so we've been thinking as much as we can about this. Let me remark before I go to the Taniyama business. Setting, we take this equation, we just complete the square really. So set psi equal 2 zeta minus 1 phi and get psi squared equal 4 zeta cubed minus 7 zeta squared plus 4 zeta. That's already coming pretty close to the Weierstrass normal form. This is sort of given to you free of essentially free of charge here, but it has another feature which is really scary, and that is that this cubic polynomial here is palindromic. It reads the same forwards as backwards, really. So, and that implies that if I do it right, there exists an automorphism of this elliptic curve E zeta phi ascending, I think it's psi goes into psi over zeta squared, and zeta goes to zeta inverse. Now, when we realize this, what is well, this tells you that from the point of view of Galois theory, because you have to do Galois theory now. You can't avoid it once you go to Taniyama. From the point of view of Galois theory, the Galois group cannot tell the difference between the zeta function and the inverse, the reciprocal of zeta function. That really makes you nervous. Could there even be any non-trivial information in this setup? Right? Anyway, that's just the way it is. That palindromic polynomial forces that. All right. Now, when we got to this elliptic curve, and somehow I think it was Peter really. I'm not really that much into some of this stuff, but no, I'm in the game really. We discovered that the conductor of this elliptic curve is 15, and that means, according to Taniyama-Vey, that this elliptic curve is closely connected in some very precise way with a gamma of 15. So I said the gamma, I'll just recall now, gamma of n is equal to the set of all A, B, C, D in gamma, such that A, B, C, D congruent to the identity matrix modulo n times m2 of z. So this is the congruence subgroup of level n, and since this curve has conductor 15, gamma of 15 it looms into the picture. Now, and then you either do some calculations of your own or go to the literature, and there is this Antwerp volume with a huge amount of information. I don't know exactly how this works really. It reminds me a little bit. The Antwerp volume reminds me a little bit of Conway's Atlas. Really. It has just a huge amount of information, and I haven't really bothered to think about proofs. But in any case, we find that, and then Fricka also comes into the game, Robert Fricka. And Sayre also put us onto this, although thinking back in the earlier decades, really, my first contact with Fricka came with the moonshine business, really, and it's really impressive. Really impressive to see the fearlessness with which Fricka carried out quite complicated numerical calculations, really. I mean, he had, for example, a 196884 and the next coefficient as well. And Peter tells me that some eager beavers have checked with the computers the calculations that Fricka carried out, and he made very few mistakes. There's some maybe, but he was really good. He was a student of Klein, and pays a great tribute to Klein in the introduction to his volume. Anyway, so Fricka proved this, that I better introduce gamma upper zero van. I'll introduce a couple of these. It's G, A, B, C, D, in gamma. Is this what I want? I'm going to do B congruent 0 mod n. And gamma 1 of n equals A, B, C, D, gamma B comes over 0 mod n, and A comes to D comes over to 1 modulo n. Well, I want to fudge a bit, and I'm going to put plus or minus 1 then. I probably created a bad error there. The reason is the minus the identity element of the modular group acts trivially on the upper half plane by linear fractional transformation, so that when you consider modular functions and just modular functions themselves, not modular forms, the minus the identity doesn't play a role. Anyway, so this is the gamma naught, gamma n. So Fricke determined the function field is generated by two. This function field is generated by two functions. It also is of genus 1. So, so it has one generator's tau, which I will write down here. I could be making a mistake, but I think I got no. 8 of 3, 8 of 5, 8 of 1, 8 of 15 cubed, or eta n of z is equal to eta of z over n. Actually, Fricke doesn't use this notation, but I think this is fairly standard now. And eta is the 24th root of the famous delta function. Whatever, I won't write it out. Anyway, this is the tau, and sigma is equal to the square root of tau to the 4th minus 10 tau cubed plus 13 tau squared minus 10 tau plus 1, with the convention that you take the positive tau has a pole at I infinity, and so this thing goes off to plus infinity as z goes off to I infinity, and so Fricke says take the positive square root along that axis. Okay, so that's this function field, and let me what I can. I want to say what I can about the what have I done? Here we are. See what I can about the function field of gamma upper 1. So gamma upper 1 of 15 generated, it has a function field with a thing which I will call Z1 and Y1. I think I have time enough to explain why I put 1 here. Z1, Y1, where Y1 squared to 4 Z1 cubed. Z1, and the relationship between the tau and the yeah, of course. Yeah, thank you. It's this same palindromic polynomial. But I'll put it this way. Now, I want to write down. I want to explain, or at least write down the relationship between this pair of functions and the tau and sigma. This we just did by brute force calculation, and it seems to agree with what's going on in the Antwerp volume. So z, so tau b1 of z1 tau plus b0 of z1 equal 0, where b0 and b1 are quartic polynomials in Z1. Now that corresponds to the fact that the way I've defined this, gamma 1 of 15, it's a normal subgroup of gamma 0, and the quotient is a cyclic group of order 4. So we have a little Galois extension of one function field by another with a Galois group, a cyclic group of order 4, and that's what the role of palindromic polynomials is. If you write down a quartic, you think, well, the Galois group probably S4. Well, in certain cases, it drops down. In this case, it does drop down. And there is an element, there exists G in gamma such that G of Z1 equals Z1 inverse. So that is capturing in the Galois theoretic setting, not particularly the setting of elliptic functions. In the Galois theoretic setting, it's capturing the fact that the Galois theory cannot tell the difference between Z1 and its inverse. That's not really a correct thing to say. I mean, Galois theory differentiates everything. It does keep track, but the fact that the Z1 and Z1 inverse are in the same orbit under the Galois group is something that, among other things, interchanges the zeros and poles of Z to 1 with the poles and zeros of its inverse. So if you're interested in zeros, you've got to be interested in poles. Okay, so anyway, we get to this. So there are the Galois group and I toss in minus the identity here for the obvious reason that that's what's going. The Galois group here acts on the function field of gamma 15, and Z1 has 96 images. The stabilizer of Z1 in this Galois group of index 96. So, and of those images, they come in pairs. And precisely one of these images has a 0 in the set E. It's a set of things E to the I theta over pi over 2 less than or equal to theta less than or equal to 2 pi over 3. So now this set, this is a part of the standard boundary of the fundamental domain, of a fundamental domain for the modular group. And so, we zeroed in on this particular one, and in the notation. So this is Z17. We actually got the explicit action of this Galois group, which is I like. It's a very pretty thing. and it's the 17th one in our numbering, which has a 0, and this 0 is simple. So the game I call these 96 images of Z1 avatars. I wanted to have a name for avatars of zeta. It has some sort of connection with the zeta function. What it is, we still scrabbling with it. It may all come tumbling down. So the game we played is this: we pick some g in gamma such that g of z17 equals z17, and we consider the union over all x in the modular group of the images of this arc. So this is we call it this is the 2-3 tree associated to gamma. You see drawings in hyperbolic pictures, what that thing looks like. Anyway, it's a geometric version of an abstract tree, and so we take the path from the 0 C of Z17 on E to G of C in the tree. Okay. So, and we consider, I just want to have enough time to say this now, we consider pairs theta z, Z17 of Z, zeta of S. No, sorry, I want to put it this way. I want to consider pairs Z, S, where Z is in the upper half plane, S is a complex number, such that Z17 of Z equals zeta of S. So this is comparing two functions, analytic functions. Now, if the Z1 and zeta were, say, if they were rational functions, then there are reasons why one might want to compare or construct algebraic varieties by taking a difference of two rational functions with distinct variables. Now, so we pick a 0 row of zeta. The huge amount of information has been accumulated over the decades on the zeros of the zeta function. And we start at the point C row. Pick a 0 row. Okay, so here the Z17 vanishes on this arc, and zeta in the row we're going to basically with the computation have been rows along the axis, real part of S equal 1/2, and follow along the 2-3 tree. Now, if you play this game, then as long as you do not run into a 0 of the derivative of the zeta function, the analytic continuation of the path is forced. We've given the recipe for what's happening on the left-hand side. It may be a stupid recipe, but that is our recipe. You follow along on that side, and if we stay away from zeros of the derivative of the zeta function, then we get a well-defined path that starts off at a 0, the zeta function. And it may wander off to the essential singularity. The zeta function has an essential singularity, of course, at infinity. And, okay, it may do that, or it may not. So we did this for the first 24 zeros of zeta in the half plane. So you just look at the tables, and you look at the first 24 zeros, they've been computed to many degrees of decimal accuracy. And Peter and Sin, this is where you have to buttonhole him, found that the path starting at nth zero goes to, or ends at the n plus first zero for 1 less than or equal to n less than or equal to 24. Of course, we have no idea what this means. I'd say the probabilities are pretty high. It means almost nothing. But I mean, I was hoping we could use the computer to test to destruction. This thing about putting curves in one function and following. But well, okay, it probably will be tested to destruction. But anyway, I wanted to be able to present this because it is something arresting. Even if it turns out ultimately to be just numerology. So that's it.
Thank you very much. Are there any questions or comments? If not, then we have 5 minutes break and start again 10 minutes past 12. Thank you very much.